Hey everybody, I really want to put students in a position to succeed on the exams. So I'm going to work through some more problems that are going to be just like problems that you will find on the upcoming exam. And so these problems that I'm going to be working on come from the 7th problem set. And the first problem is going to be problem number 4. And so per usual, we want to start by writing down the things that we are given. We are told that there's a chair, and so I'm going to say the mass of the chair is equal to 35.6 kilograms. We are told that when the chair is placed on a spring and it oscillates with simple harmonic motion, that the period of that oscillation is equal to 1.30 seconds. Now, when it comes to waves and simple harmonic motion, the period is the number of seconds in one cycle of the oscillation. And by cycle, these waves repeat themselves. They go from peak to valley to peak to valley to peak to valley and so on. And so one cycle is going from peak to valley back to peak again, going back to where you started. Or you can go from valley to peak back to valley again. That's a cycle. And so the idea is how much time elapses from going from peak to valley back to peak. How much time in one cycle. So period is the number of seconds in a cycle. Just so you know, there's another expression for waves we call frequency. And so if period is the number of seconds in a cycle, frequency is just the reciprocal of it. It's the number of cycles in a second. There's an inverse relationship between period and frequency. Period is the number of seconds in a cycle. Frequency is the number of cycles in a second. So we're told that the oscillation period for the chair attached to the spring is 1.3 seconds. And ultimately, we're going to have an astronaut that sits in the chair. And so the C plus A is the chair plus astronaut. When the astronaut sits in the chair and there's oscillation with the spring, the period increases to 2.23 seconds. So part A, what we are asked is to solve for the spring constant K. Now, a little bit more detail here. You can think of that being a spring, and then at first there's going to be a chair that's placed on this spring. And so when that chair is placed on that spring, the chair has some mass, which means that the spring squishes a little bit, which means that because of Hooke's law, the spring is going to push back up on the chair that's being pulled down by gravity. And so what happens is you're going to have this oscillation back and forth. You can imagine the spring squishes and then pushes back up, and then it goes past its rest position and goes higher, and then it comes back to the rest position and then it squishes again. And so that red, you can imagine, is going to be the back and forth oscillation. And so you can think of the oscillation, the lowest the chair goes is, say, a valley, and the highest the chair goes is a peak. Okay? And the distance from the rest position to either a peak or a valley is the amplitude. So you are given an equation sheet for the exams. And when you look at simple harmonic motion, you will find an expression for the frequency of simple harmonic motion. And more specifically, since we were started by putting the chair in the spring before the astronaut comes into the picture, so I'm going to say that the frequency of the chair, and again, this comes from your equation sheet that you have for the exam. So 1 divided by 2 pi times the square root of the spring constant K divided by the mass that's oscillating. In this case, it's just the mass of the chair. Now, you can see above, we already know what the mass of the chair is. We know what 2 pi is. So what we need to do is we need to solve for K. I mentioned that the period T is the number of seconds in a cycle, and that's the reciprocal of the frequency, which is the number of cycles in a second. So I can say that the frequency of the chair's oscillation on this spring is equal to 1 over the period of that oscillation. Because again, frequency is cycles per second, period is seconds per cycle. So now what I'm going to do is a little algebra. I'm going to multiply both sides by the period of the chair oscillation. And so when I do that, I'm going to get T chair is equal to 2 pi. If I multiply both sides by 2 pi, I'm going to get a 2 pi in the numerator. And if I divide both sides by the square root of k over mc, then I'm going to now get the square root of k over mc in the denominator. So I hope you can see I took that expression for frequency and related it to period. I multiplied both sides by tc. I multiplied both sides by 2 pi. I divided both sides by the square root of k over mc. Now, right now I have a square root sign and I want to get rid of that. So to get rid of that, what I'm going to do is I'm going to square both sides. So the period of the chair oscillation squared is going to be equal to 2 pi squared. And now because I'm squaring something that has a square root, I just get what's under the square root. And so that means that I'm just going to have k divided by the mass of the chair. So we ultimately want to solve for k. And so it's going to make sense to try to isolate for k. And so to do that, what I want to do is I want to multiply both sides by k over mc. So I'll have k over mc multiplied by the period squared equals 2 pi squared. Now what I can do is I can divide both sides by tc squared such that I'll have k divided by mc equals 2 pi squared divided by tc squared, which I could simplify as just saying 2 pi over tc squared, because that's both the numerator and the denominator squared there. And then since I want to isolate k, I can multiply both sides by the mass of the chair such that I'll get k is equal to 2 pi divided by the period of the chair's oscillation and multiplied by the mass of the chair. And so that is enough to solve, because this mc right here I have right here. I can plug in that value, and this tc right here I have right here. So you can plug in the values there and make sure that we have the square sign there. So I can write that out even more explicitly. I can say 4 pi squared over t chair squared mc. And so you plug those numbers in and you're able to solve for k. So that's part A. And so the continuation of number 4 for part B, we ultimately are asked to solve for the mass of the astronaut. So what's going to happen, you can imagine that you have a chair oscillating on a spring. Well, imagine that same spring, imagine the chair, but then imagine now an astronaut sitting in that chair. There's more mass now that's oscillating. You're still going to have an up and down oscillation, but our frequency is going to be different. And more specifically, the frequency of the simple harmonic motion is now a chair plus astronaut mass. And again, you can look up this equation for simple harmonic motion in your equation sheet that you have on exams. And so this k, remember, we already solved for in part A, so that's going to be helpful for us. This right here is the k. And so we have to make sure that we account for both the mass of the chair plus the mass of the astronaut now. You see how in part 1 it was just the mass of the chair right here. Now we have to account for both the mass of the chair and the mass of the astronaut. And again, remember, frequency is going to be cycles per second, so period is seconds per cycle. So this is equal to the reciprocal of the period, and I'm going to call it period C plus A. C plus A. So this is going to be similar algebra to what we did in part A. It's just that our mass is different now, but we have something going for us now in that we already know what K is. So that's going to be the ticket to eventually solve for the mass of the astronaut. So I want to get rid of the square root sign. So to do that, I'm going to square both sides of the equation. And when I square both sides of the equation, that means that I get 1 over 2 pi squared k divided by mc plus ma. K, again, is a spring constant. We know what it is. We solved for it in part A. Equals 1 over t c plus a squared. I squared both sides of the equation. Now, long-term goal here is I want to isolate for ma, which is the mass of the astronaut. That's what we're asked to solve for. So what I'm going to do now is a little bit more algebra. I'm going to, because I ultimately want to solve for ma, I want to get ma up in the numerator somewhere. So I'm going to multiply both sides by the quantity mc plus ma. So I'll have 1 over 2 pi squared k equals mc plus ma divided by t c plus a squared. And now I multiply both sides by the period of c plus a squared, such that I'll have 1 over 2 pi squared k t c plus a squared equals mc plus ma. Getting close to isolating ma now. So now what I'm going to do is I'm going to subtract both sides of the equation with an mc. So what I will have is ma equals 1 over 2 pi squared k t c plus a squared minus mc. Now I have isolated the mass of the astronaut, and I can simplify this even further. So going back to part A, it looks like I got a little eraser here. I'm going to put that back. That is the t of the chair squared. K was equal to 4 pi squared mc tc squared. So I can plug that in for k right here. And so this is going to be equal to 1 over 4 pi squared. I'm just going to actually square that term. And remember, k is equal to 4 pi squared over the period of just the chair squared times the mass of the chair. And then I have my t c plus a squared minus mc. And now I'm going to get some simplification. The 4 pi square terms are going to cancel each other out. And that means I can rewrite this because you see there's the mass of the chair term here and here. I'm going to factor out the mass of the chair such that I'll have a TC plus A divided by TC. They're both squared, minus 1. I hope you can see how I move to this next step by taking the mass of the chair. Since it appears in two different terms, I can factor it out, and if you were to multiply it through, you would have it in both of the terms that you see in those brackets. And so at this point, we are going to just need to plug in numbers, because we have a mass of the chair term, and that, as you see, we already have been given right here. We have both the period for the chair plus astronaut and for the chair. We are given both of those terms. You see the two terms right here and right here. And of course we know what 1 is, and so all we need to do is plug those numbers in, and we solve for the mass of the astronaut. So this is a simple harmonic motion problem. A key move in this problem is recognizing that you can express the frequency of a simple harmonic motion as the reciprocal. That is, 1 over something is the reciprocal. So the frequency is the reciprocal of the period. Frequency is going to be the number of cycles per second, and so the reciprocal of that is the number of seconds per cycle, and the period is the number of seconds per cycle. Moving on. Question number 5, and again, this is from homework number 7. And so in this problem, let's go ahead and write down what we're given. We're given a mass equal to 1.85 kilograms. We're given a spring constant. We're just given it this time. In the previous problem, we had to solve for it in part A. Now we're given 330 Newton meters. Those units should make sense, because remember, Hooke's law is kx. So if you displace a spring, then the spring's going to push back with a force that's equal to the spring constant k multiplied by how much you displace the spring from its rest position. And so think about kx. So if k is in newtons per meter and x is in meters, then kx Newton meters multiplied by meters would be newtons, which would make sense because force is in newtons. We're also told that this mass has an initial velocity. It's going to the left, so I'm going to give it a negative sign, and it's 15.0 meters per second. So the speed would be 15 meters per second. The velocity would be 15 meters per second to the left horizontally. So we'll call positive x to the right, positive y up and down. Just to illustrate what's going on here, you can imagine if I had a spring, and then that spring was connected to some mass. That mass initially, m, has some initial velocity, we'll say v naught, and it's going to the left, and so that's negative 15.0 meters per second. Now, if you can imagine, that spring is going to squish up. I'll draw the mass. The mass doesn't change, but there's been a change in the position of the mass, and that's delta x. I'll make that more clear. Delta x. This is the change in the horizontal position from right at the beginning of the problem to when the spring gets squished by a certain amount. Then it pushes back. And when it pushes back, I'm going to draw another picture where it gets right back to the original location. And then you can imagine at some later time, the mass has moved even further to the right. And it's just going to oscillate back and forth, left to right, left to right. So that this delta x right here is the same as this one. It's just in the other direction. And so in both those cases, those delta x's you can think of as the amplitude of the oscillation. And you can think of The spring, when it's at its relaxed length, is an equilibrium position, and it's going to get squished a certain amount, go back to equilibrium, and then it's going to stretch out a certain amount. And both the squish maximum and the stretch maximum are the same. They're the amplitude. So I've got 4 different times here. We're going to say that the initial time, that's the initial setup of the problem. The mass is moving to the left, 15 meters per second. It's going to keep moving to the left until eventually the squishing of the spring stops. And there's a moment where the velocity of the mass, which I'm going to call v1 here for time 1. So v0 is initial time, v1 time 1, that's 0. Because there's a moment where it comes to a stop before it starts moving back to the right. Then it's going to go back to its equilibrium position, and this, we'll call it v2, is going to be precisely the same magnitude as the initial velocity, just in the opposite direction. This is similar to when you say throw a stone straight upward. Eventually gravity, which is pulling downward, slows that upward trajectory to a point where the stone comes to a momentary stop, i.e. the velocity 0. Then it begins to fall back down. Just as it took a certain amount of distance for gravity to get it from a velocity to 0, if it covers that same distance and it's the same old gravity working, it's going to go from 0 back to whatever that speed was, just in the opposite direction. So the vector is in the opposite direction, the magnitude is the same. Same thing here with the spring. And so then eventually the spring is going to stretch out, and the stretching is going to slow it down, and it's momentarily going to come to rest before it starts to squish again. So v3 is 0. So you can see that we've got a kinetic energy at time 0 and at time 2. At time 1 and at time 3, there's no kinetic energy, which means that because only conservative forces are acting here, that there should be elastic potential energy at those times and no kinetic energy. So what we can say is that at the initial time, we have 1/2 m v0 squared. And that is the kinetic energy right at the beginning. The spring is at its rest length, so there's no change in elastic potential energy yet. But then at time 1, when the motion of the mass is momentarily stopped, then I'm going to put this on the other side of the equation. The original energy that was all in the form of kinetic energy would then be in the form of 1/2 k delta x squared. And again, the delta x is how much the spring squished from the beginning to the time where the mass momentarily comes to a rest before it starts to go back to the right. So what I just wrote is a conservation of energy equation. Originally, all the energy is kinetic, and then at a later time, there's no more kinetic energy, and that energy went into elastic potential energy. Mind you, there are forces acting in the vertical direction here, but if this was, say, on a table, then even though gravity is acting down, the table's pushing back up. So we're just focusing on the horizontal direction. So ultimately, I need to solve for what my displacement delta x is, which, as I said, is essentially the amplitude of this oscillation, where you're going to have the position of this mass relative to the relaxed length of the spring. There's going to be a time where the spring has compressed its maximum amount, so the distance from equilibrium to that is an amplitude. And then there's also going to be a time where the spring has stretched out past its equilibrium, and that is going to be the same exact amount, just in the other direction. So either way, we call it the amplitude. So we don't have to worry about the sign here. We can treat it as a scalar. Now, continuing to solve for this problem, I can already rule out 1/2 because both sides of the equation have it. And now what I'm going to do is I want to solve for delta x, and so it makes sense to try to get that on one side of the equation. And so I can say that delta x squared is equal to m v0 squared divided by k. So what I did was I simply divided both sides of the equation by k. Now I want to get rid of the square, and so I can say, and remember, with a square you can have a negative number or a positive number. Squared is going to be a positive number. But I want to just to be clear here, I'm going to put absolute value, because it doesn't matter if we're talking the amplitude when the spring is squished at its maximum or when it's stretched at its maximum. We call both of those displacements from the equilibrium the amplitude. It doesn't matter which side you pick. The amplitude is the amplitude, it's a scalar. So when I put the absolute value, this is just to say that I'm going to make sure that my answer for the amplitude I report is positive. And so I need to take the square root of both sides. So I take the square root of the mass times the initial velocity divided by k. So since I have underneath the square root a square term, that term actually can come out, and I'm going to call that the absolute value of v naught, just to be clear here that this is positive, because technically you could have a negative velocity there squared and it would also be positive, and that is multiplied by the square root of m over k. And so we have been told what our initial velocity is, and since again I'm telling you the amplitude is a scalar, don't worry about the sign, the absolute value of negative 15.0 square root of m over k is just 15.0, because it's the absolute value, times the square root. We're told the mass is 1.85 kilograms, and k is 330 Newton meters. And so when you plug all those numbers in, you get approximately 1.12 meters. So conservation of energy was the ticket here. We had to realize that at some initial time, all of our motion is in the horizontal direction, and since the spring is at equilibrium, our energy is in the form of the kinetic energy of the mass, 1/2 mv squared. And then at some time later, you can imagine, because the spring is starting to squish, it's pushing back to the right, which is slowing the mass down as it moves to the left, less and less and less velocity to the left, to a point where there's at a moment zero velocity before it starts to go back to the right. So at that time where it's momentarily at rest, we say v1 equals 0, which is to say the kinetic energy of the mass is 0, which is to say that the original kinetic energy of the mass has now gone into the elastic potential energy of the spring. It's energy that's stored up in the spring, such that now the spring can do positive work on the mass, pushing it back to the right. So that licensed me to write this equation right here. This was the key. You have all kinetic energy on the left, you have all elastic potential energy on the right, and then I can simplify and eventually plug in the numbers that were given to solve for delta x. And remember, amplitude, it doesn't matter whether you're talking about a peak or a valley. Amplitude for oscillations, i.e. waves, is going to be the distance from the equilibrium position to the maximum, or the distance from the equilibrium position to the minimum. Now, I'm going to do one more problem for you. Again, this is from problem set number 7, and this is problem number 7. And this is another problem that gets at some important concepts when it comes to waves. And so, by waves, you know, I've been talking about peaks and valleys and peaks and valleys. So imagine we have some oscillation. This is a peak right here. This is a crest or a valley. Okay, this is a peak. This is a crest. This is a peak. This is a crest. So when you talk about the wavelength of a wave, it's going to be the distance from either peak to peak, such as right here, or valley to valley, right here, because that's a cycle. The wavelength is the total distance that's covered in one cycle. Now, I also mentioned this idea of frequency. Frequency is how many of those cycles you have per second. And this is equal to the reciprocal of the period, because the period is the number of seconds in one cycle. Frequency, cycles per second, is given in units of hertz. So the dimension on frequency is hertz, which is cycles per second. And the dimension for period, seconds per cycle, is just going to be seconds. So for frequency, you use units of hertz. For period, you use units of seconds. Frequency is cycles per second. Period is seconds per cycle. And then the wavelength dimension is just meters. It's just a distance. It's a distance from a peak to a peak or a valley to a valley. It's the distance of one cycle. So in this problem, we are told that there's a fisherman and the fisherman's boat is going up and down, and the key here is periodically. That tells us it's a wave. And so it turns out that we have delta t equal to 2.90 seconds for the boat to go from its highest to its lowest. So 2.90 seconds from peak to valley. That would be like going from right here to right here. That would be 2.9 seconds. So that is not a full cycle. That is just half of a cycle. A full cycle would be going from peak to peak. So we know that the time going from peak to valley is 2.9 seconds. So that means that the period, which is the amount of time for a full cycle, divided by 2 is equal to 2.90 seconds. Again, from here to here, that's just half of a period. A full period would be from here to here. So half of a period is 2.90 seconds. So that's key. And then in this problem, we're told that the distance from the highest point to the lowest point is going to be 0.610 meters, which is to say, I'm going to draw this dotted line. The distance of 0.610 meters is the distance from right here to right here. Now, here's the key. So 0.610 is the distance from here to here, but the amplitude is from equilibrium to peak or from equilibrium to valley, which is to say that the amplitude A is equal to 0.610 divided by 2. This is the key. That 0.610 that we're told, that's from the highest point to the lowest point. But amplitude is from equilibrium to highest or from equilibrium to lowest. That's why I divide by that total distance by 2. So the amplitude is going to be 0.610 divided by 2. Another important piece of information is we are told that apparently this fisherman has noticed that there are 7.80 meters from crest to crest, from peak to peak. The spacing is 7.8 meters. Same thing would be the case from valley to valley, like this 7.80 from here to here. So for part A, we want to know how fast the waves are traveling. Remember, velocity, meters per second. okay? And so it's going to make sense that for the wave, we have a velocity v. This is the wave velocity. It's equal to how far it is from peak to peak or from valley to valley. I'm just going to call this delta x divided by the period, which is the amount of time that elapses from peak to peak or valley to valley. So this is for one cycle. And so it turns out that for one cycle, that change in x is just simply the lambda divided by t, the wavelength, the distance from peak to peak, or the distance from valley to valley, divided by the time it takes to go from peak to peak or valley to valley. And we already know what t is because t over 2 is 2.90 seconds. So t is equal to 2.90 seconds multiplied by 2. Okay, so that should be 5.80 seconds. And we are told that our lambda, the distance the fishermen determined from crest to crest, is 7.80 meters. And so this is simply 7.80 meters divided by 5.80 seconds. And you should get approximately 1.34 meters per second. By the way, when you see on the exams problems that say express your answer after 2 decimal places, I mean 2 places past the decimal point. So I just did that right there. 1.34 is an expression out to 2 decimal places. Part B of the problem is now asking, what is the amplitude? And I actually already went through this. The amplitude, again, is the distance from the equilibrium position to the max, or the crest, if you want to call it. Or it can be thought of as the distance from the equilibrium position to the trough or the valley. So this green, that right there is the amplitude from equilibrium to the max. And this orange right here is the amplitude from equilibrium to the trough. And we were told that the total distance, both the green and the orange there, was 0.610 meters. And so remember, amplitude is only half of that total distance from peak to valley. And so it's 0.610 meters divided by 2. The green or the orange will be the same amount. It's just one is going from equilibrium to the max, one's going from equilibrium to the min. You can think of the max as a crest, and you can think of the min as a trough, or you can think of the max as a peak and the min as a valley. So oscillations, i.e. waves that repeat themselves over and over and over again, have been a key concept for these problems. And so remember, since these things are repeating themselves over and over, there's a certain amount of distance that's covered from the peak to when we start another peak, which is one cycle, or from the valley to another valley, one cycle. That's the wavelength. We say that going from a peak to a peak or a valley to a valley is a cycle, and so frequency is a gauge of how many cycles we have in a single second. You can think of high frequency as having many short wavelengths repeating in a second, whereas you can think of low frequency as the wave being stretched out. You don't have as many cycles in a second. The more cycles you have, the more squiggly the wave is going to look because it's repeating itself more frequently in a second. So high frequency, think of the wave as very like squiggly, lots of cycles in a second. Low frequency, think of it as really stretched out, not as many cycles in a second. And so it's one thing to talk about cycles per second, which we give in hertz, but then we can also talk about seconds per cycle. How many seconds does it take for a wave to go from peak to peak or from valley to valley? And that is the period. And the period and the frequency are inversely related to each other. Frequency is cycles per second, period is seconds per cycle. So you could say the frequency is 1 over t, or you can say t is 1 over f. Hope you found this helpful. Wish you all the best.